Okay, so good evening. This is the sixth live discussion session, problem solving session of the course Geotechnical Engineering 1. The topic of today's discussion will be flow through soils, quicksand conditions. So, like the previous sessions, in this session also, I have given a set of questions. In this particular session has 20 questions, a combination of MCQs, MSQ, multiple select questions, some true false statements, and a few numericals. Okay, so I don't remember whether the person who has joined, whether you have joined the previous classes, whether you in the previous classes, but generally uh, I first start with dictating the questions. Okay, I first dictate the questions till the end, and you need to write down the questions along with the options, you know. So during that time, you will just write down the questions as I dictate, and after that, I will give you some time, generally 15 to 20 minutes, depending upon the complexity of the problems I've given. So after that time, I'll start with the solutions. I'll ask you each and every question. If you have solved the question, you can tell me whether you have solved the question or not. You can tell me the answer. Otherwise, I am going to tell you the solutions. I'm going to give you the solutions anyway, and I'm going to also explain the concept behind the solutions. Okay. So this is how these sessions go generally. Today also it will be the same case. This session has 20 questions. So I would first start with dictating the questions. You will write down the questions, and after that I will give you 15 minutes time to solve them. You'll stay in the meeting. Okay, don't leave the meeting. After 15 minutes, I'll start discussing the solutions, and then you can tell me how you have solved the problems. Okay. So I will directly go to the PPT right now. Yes, I hope this is visible to you. If it is not visible to you, please raise your hand or please stop me and ask me if there is any query, or you can also write in the chat box if you have any query regarding the questions or understanding what I'm saying or seeing the questions, anything. Okay. So okay, I'll start with dictating the questions one by one. I think another person has joined. Yes. I cannot see the person who has joined. Anyway, so good evening once again. This is the sixth problem solving session of the course Geotechnical Engineering 1, and the topic of today's session is flow through soils, quicksand condition. Okay, so I'll start with dictating the questions. Please write down the questions and the options very carefully, and I hope you are sitting with your calculator also, because this session also has numericals. So the first question is, yes, quicksand condition occurs when? Quicksand condition occurs when? Your options are: effective pressure becomes less than 1. Option 2, effective pressure reduces to 0. Option 3, effective pressure is equal to atmospheric pressure. and last option is none of these. I repeat the question. Quicksand condition occurs when? First option, effective pressure becomes less than 1. Second option, effective pressure reduces to 0. Third option, effective pressure is equal to atmospheric pressure. And last option, none of these. Okay. Next question. Yes. Soils most susceptible to piping failure are soils most susceptible to piping failure are. Your options are inorganic clays, coarse sands, fine sands and silts, or gravels. I think someone else has joined. I think 3 people have joined, but I can only see 2 in the window. Anyway, this is the second question. I repeat the question. Soils most susceptible to piping failure are. The options are inorganic clays, coarse sands, fine sands and silts, or gravels. Okay. Next question. The line within a dam section below which there is positive hydrostatic pressure. The line within a dam section below which there is positive hydrostatic pressure. The options are cutoff line, phreatic line, flow line, or pressure line. Yes, ARV. Any query?
The dam it is mentioned, but it is not mentioned as a earthen dam.
Yeah, you just assume the things. See, this is a chapter specific question. It is not like gate where you'll get questions from different subjects and different chapters of the same subject. So by dam, we know there are many kinds of dam: gravity dam, concrete dam, rock fill dam, earthen dam. Okay, but since this question, a set of questions is chapter specific, so when I say a dam, there will be a line below which there is positive hydrostatic pressure. Then assume that it is an earthen dam. Okay, because this question is related to this chapter. See page. Okay. Yeah, so the question was the line within a dam section below which there is positive hydrostatic pressure. Okay, the options are cutoff line, phreatic line, flow line, or pressure line. Okay, next question. Yes, soil at the toe of a dam has void ratio 0.62. G, that is the specific gravity of soil solids, G is equal to 2.62. Assuming a factor of safety of 5, the permissible exit gradient is, the permissible exit gradient is, the options are 1, 0.5, 1.05, or 0.2. I repeat the question. Soil at the toe of a dam has void ratio 0.62, G equal to 2.62. Assuming factor of safety of 5, the permissible exit gradient is, first option is 1, second option is 0.5, third option is 1.05, last option is 0.2. Okay, next question. Yes. The value of hydraulic gradient corresponding to zero resultant body force is, first option effective hydraulic gradient, second option total hydraulic gradient, third option critical hydraulic gradient, last option is zero hydraulic gradient. I repeat the question. The value of hydraulic gradient corresponding to zero resultant body force is, the options are effective hydraulic gradient, total hydraulic gradient, critical hydraulic gradient, or zero hydraulic gradient. Okay. Next question. Yes, this is a multiple select question. It can have more than one correct answer. Elevation of a point with respect to any arbitrary datum is called. Elevation of a point with respect to any arbitrary datum is called. The options are pressure head, position head, total head, or elevation head. I repeat the question. Elevation of a point with respect to any arbitrary datum is called. The options are pressure head, position head, total head, or elevation head. And I repeat, more than one option can be correct in this question. Okay. Next question. Yes. Equipotential lines represent contours of. Equipotential lines represent contours of. First option, equal density. Second option, equal viscosity. Third option, same path. Last option, equal head. I repeat the question. Equipotential lines represent contours of, the options are equal density, equal viscosity, same path, or equal head. Okay. Next question. Again, another MSQ. The path along which individual particles of water seep through soil is called. The path along which individual particles of water seep through soil is called. Your options are flow lines, path lines, traverse, or stream lines. I repeat the question. The path along which individual particles of water seep through soil is called. First option, flow lines. Second option, path lines. Third option, traverse. Last option, stream lines. And I repeat, more than one options in this case can be correct. Okay. Next question. Yes. Grains in the soil below hydraulic structures gets lifted when the critical hydraulic gradient is greater than the exit gradient. I repeat the statement. Grains in the soil below hydraulic structures get lifted when the critical hydraulic gradient is greater than the exit gradient. Is this statement true or false? I hope you have idea about critical hydraulic gradient and exit gradient. If you have any doubt regarding the questions while I am dictating, you can just stop me and ask, or raise your hand, or drop a message in the chat box. Okay, I repeat this statement. Grains in the soil below hydraulic structures gets lifted when the critical hydraulic gradient is greater than the exit gradient. So is this statement true or false? You have to say. Okay. Next question. Yes. The portion between two successive flow lines is called. The portion between two successive flow lines is called. Here you can obviously you have to tell the right answer. It is an MCQ, only one option is correct, or if there is any other answer in your mind, you can also say that. Sometimes there can be more than one nomenclature. I repeat the question. The portion between two successive flow lines is called. First option, flow gap. Yes, first option, flow gap. Second option, stream gap. Third option, flow channel. Last option, none of these. Next question. Yes, this is a numerical. Write down the data very carefully. You can also take a screenshot. In a flow net, there are 4 flow paths and 15 equipotential drops. If the head loss is 3 meter and K, what is K? K is the coefficient of permeability. K equal to 2 into 10 to the power minus 5 meter per second. Estimate the quantity of seepage in meter cube per second. That is discharge per unit time. The flow net has 4 flow paths, 15 equipotential drops. The head loss is 3 meter. The coefficient of permeability is 2 into 10 to the power minus 5 meter per second. You have to find out the quantity of seepage. The options are 4.2 into 10 to the power minus 5, 2.2 into 10 to the power minus 5, 1.6 into 10 to the power minus 5, or 4.2 into 10 to the power minus 4. Okay. Okay, I'll just repeat it once. Write down the question. I repeat the question. In a flow net, there are 4 flow paths and 15 equipotential drops. If the head loss is 3 meter and K equal to 2 into 10 to the power minus 5 meter per second, estimate the quantity of seepage in meter cube per second. Okay. Excuse me. Next question. Yes. Again, a true false statement. For a two-dimensional flow, it is assumed that the porous medium is incompressible. Is this statement true or false? In this question, uh, try to remember the fact that in the theories, in the concepts of seepage and permeability, we the primary thing we need to find out the discharge, the seepage, and the and or the coefficient of permeability. So there's an equation given by Darcy's law, and the Darcy's theory has some assumptions. So that assumption is for two-dimensional flow, and whether the porous medium is incompressible, this is an assumption or not. That is the statement over here. I repeat, for a two-dimensional flow, it is assumed that the porous medium is incompressible. So you have to say whether the statement is true or false. Okay. Okay. Next question. Yes. Seepage pressure is, first option, equal to pore pressure. Second option, impact pressure of precipitation on soil. Third option, pressure exerted by percolating water on the soil. Last option, none of these. I repeat the question. Seepage pressure is, it is simple, it is asking the definition of seepage pressure. The options are equal to pore pressure, impact pressure of precipitation on soil, pressure exerted by percolating water on the soil, or none of these. Okay. Okay, I'll go to the next question. Yes. A homogeneous earth dam is 52-meter high with 2-meter freeboard having 25 equipotential drops and 4 flow channels. If the coefficient of permeability is 3 into 10 to the power minus 3 centimeter per second, calculate the discharge in meter cube per second per meter length. The options are 0.00036, 0.00024, 0.0036 or 0.0024. All the options in meter cube per second per meter length of the dam. I hope you have written down the question. Anyway, I'll repeat the question once. A homogeneous earth dam is 52-meter high with 2-meter freeboard having 25 equipotential drops and 4 flow channels. If the coefficient of permeability is 3 into 10 to the power minus 3 centimeter per second, calculate the discharge in meter cube per second per meter length. A similar sum has been already given previously in this same session only. There is a slight change or modification in this sum, very minor. The options are 0.00036, 0.00024, 0.0036 or 0.0024. Okay, I hope the question was clear. There was no doubt regarding the question. Now, okay, next question. Yes. Which one among the following is a scalar function of space and time whose derivative with respect to any direction gives the fluid velocity in that direction? I repeat, which one among the following is a scalar function of space and time whose derivative with respect to any direction gives the fluid velocity in that direction? Okay, your options are stream function, scalar velocity, potential function, or velocity potential. I repeat the question, which one among the following is a scalar function of space and time whose derivative with respect to any direction gives the fluid velocity in that direction? So when we differentiate that scalar function with respect to any particular direction, what do we get? We get the fluid velocity in that direction. So which among these is that function? Option 1, stream function. Option 2, scalar velocity. Option 3, potential function. Or option 4, velocity potential. Okay. Okay. Next question. Yes, this is the question. Okay. Portion between two adjacent equipotential lines and adjacent flow lines is called. I repeat, portion between two adjacent equipotential lines and adjacent flow lines is called. Your options are field, gap, potential drop, or velocity drop. I repeat the question, portion between two adjacent equipotential lines and adjacent flow lines is called. The options are field, gap, potential drop, or velocity drop. Okay. Next question. Just a minute. Yes. The hydraulic head that would produce quick condition in a sand stratum of 2 meter thickness if G equal to 2.7 and E, that is the, what is E? E is the void ratio. E is equal to 0.7 is. I repeat, the hydraulic head that would produce quick condition in a sand stratum of 2 meter thickness if G equal to 2.7 and E equal to 0.7 is. First option is 0, second option 1, third option 2, or fourth option 3. Yes, someone raised a hand. ARB.
Sir, I think all the units are in meters options.
Yes, in the options, what? Yes, all the units are in meters. Yes, yes,
Okay, sir.
yes. All the units in this, wait, yeah. All the units in this, in the options, they are in meters. Okay. To find out the hydraulic head in meters. I repeat the question, the hydraulic head that would produce quick condition in a sand stratum of 2 meter thickness if G, that is specific gravity, equal to 2.7 and E, that is the void ratio, is 0.7 is. The options are 0, 1, 2, or 3. All the options are in meters. Okay, next question. Yes. The critical hydraulic gradient for a loose deposit of sand having specific gravity of 2.67 and void ratio of 0.67 is. A similar question, a bit different answer. I'm seeking over here. Options are all the same. Here I'm talking about the hydraulic gradient. Okay. The options are 0, 1, 2 or 3. I repeat the question. The critical hydraulic gradient for a loose deposit of sand having specific gravity of 2.67 and void ratio of 0.67 is, options are 0, 1, 2 or 3. Okay. Next question. Yes. Write this down very carefully, or you can take a screenshot of this image. So there is one mistake over here. I'll just sort it out. See, this is 8 meter excavation and this is Z equals to 4.5. It won't be 12. You won't be needing this anyway. Okay. So the question is, sorry. Yeah. The question is, the sand stratum is overlain by saturated clay having unit weight 18.5 kilonewton per meters cube. This clay has this unit weight. Okay, this is sand, this is clay. At 8 meter excavation depth, water started entering the trench from below. And when I say water started entering the trench, that means obviously a crack has been developed. Okay, a crack has been developed. So this is a condition of piping failure. Okay, taking unit weight of water as 10 kilonewton per meter cube, calculate the height in meters to which water would have risen from the top of the sand in a borehole if it were drilled prior to the excavation. So I'm just telling you for your sake. So since the borehole was drilled prior to excavation, at this level it was drilled so that it is easier for us to measure the pore pressure. Okay, measure the pore pressure or the seepage pressure over here. Now since this clay layer I have already mentioned saturated, okay, you know what is the condition of piping failure. Just apply that and find out the height of this water in this borehole which was drilled prior to the excavation. Before the excavation it was drilled. Okay, the options are 8.839, 7.328, 8.325 or 7.632. As I mentioned, all the values are in meters. Please let me know if you have written down this question or copied the data in any way, whether in writing or in screenshot, whatever. Is it done? Not the sum, but copying the question. Is it done? Have you copied the question? And the diagram? Hello. Okay, fine. So
Yes, sir.
yeah. Okay, fine. So this was the question. A clay having unit weight 18.5 at 8 meter excavation, water started entering the trench. The water unit weight is 10. There is a sand layer beneath the clay layer. Okay. So find out the height in meters to which the water would have risen in the top of the sand in a borehole that was drilled before the excavation started. Okay. Last question. Another numerical. You can write down the data. So water is flowing at a rate of 0.04 ml per second in an upward direction through a fine sand. So here there is water in the sand, but the water is flowing in an upward direction in the fine sand. Sample whose coefficient of permeability is 2 into 10 to the power minus 3 centimeter per second. Okay. The sample thickness is given as 10 centimeter, cross sectional area as 45 centimeter square, and its saturated unit weight is 1.93 gram per cc. Okay. So in these conditions, you have to first determine the head causing the flow in centimeters, and then you have to find out the effective stress at the bottom of the soil. The data you have to write down is the flow rate 0.04 ml per second. Ml means cc, 0.04 centimeter cube per second. K, that is the coefficient of permeability, as 2 into 10 to the power minus 3 centimeter per second. Sample thickness, or L, as 10 centimeter. The cross sectional area A as 45 centimeter square. Saturated unit weight gamma sat as 1.93 gram per cc, and obviously you know gamma w in gram per cc or rho w in gram per cc is 1 gram per cc. Okay. So here you have to first find out the head causing the flow. Obviously you will be using Darcy's law, and then at part B you have to find out the effective stress at the bottom of the soil, keeping in mind that in this case the water is flowing in an upward direction. The water is flowing in an upward direction. Okay. Please let me know once you have copied the question. Water is flowing at a rate of 0.04 ml per second in an upward direction through a fine sand sample whose coefficient of permeability is 2 into 10 to the power minus 3 centimeter per second. The sample thickness is 10 centimeter, cross sectional area is 45 centimeter square, and its saturated unit weight is 1.93 gram per cc. Determine the head causing the flow in centimeters and the effective stress at the bottom of the soil in gram per centimeter square. Have you finished copying the question? Okay. Okay. So I'll give you 15 minutes or 10 minutes. How much time do you want? I'll start at 7:10 if it's 10 minutes, if it is 15 minutes. So how much time do you want? 10 minutes. Okay, very good. So I'll be starting the discussion part at 7:05. Okay. Yeah. Am I audible? Hello. Am I audible? Okay. So I'll start with the discussion part of this session. Okay. I hope you have solved the questions by now. Okay. So let's start. The first question was, yes, quicksand condition occurs when? What is the answer? Quicksand condition occurs when? What is the answer? Okay, so the answer over here is effective pressure reduces to zero. Effective pressure reduces to zero. The soil loses all its shear strength. Okay, so when this happens, then quicksand condition comes into action. Okay, so quicksand condition occurs when the effective pressure reduces to zero. Okay, next question. Soils most susceptible to piping failure are. What is the answer? Soils most susceptible to piping failure are. What is the answer? 2C. Yes, very good. Fine sands and silts. Fine sands and silts. Why? Because in this kind of soil, there is a continuation of the pores for which the soil can seep through upwards. Okay. Clays, what happens with clays? Clay, they are porous but not permeable. Okay. Too small pores for the water to pass through. And what happens in coarse sands and gravels? In coarse sand and gravels, because of their high, you know, grain size, there is a discontinuity in the pore spaces. Okay, and the seepage path, it breaks. It is not consistent. It's intermittent. Okay, but in fine sand and silts, seepage is possible because there is continuation of the pores. Okay, so fine sand and silts are more susceptible to piping failure. Okay.
Sir, excuse me, sir.
Yes.
Does it mean that fine sand and silt will have a laminar flow?
Laminar flow. Laminar flow and turbulent flow, it is
It is not relevant here.
not relevant here. Okay, not relevant here, of course, but you only think that turbulent flow will cause more, what to say, damage,
Turbulent flow? Yeah,
more
turbulent
damage.
flow is.
Yes,
Yes,
yes.
sir. Yes. Gravel and sands will have a turbulent flow.
Yes, that is the thing. Laminar flow, when the soil is just smoothly seeping
Okay.
upwards, that will, I think, it will cause more trouble. Okay, because
Okay.
in the case of turbulent flow, there is the flow is breaking. That
Yes, sir.
will be observed in, as you mentioned correctly, core sands and gravels. Right.
Okay, sir.
Yeah. So the answer is fine sands and silts over here. Okay, next question. Okay, the line within a dam section below which there is positive hydrostatic pressure. Of course, it is an earthen dam over here. I'm considering. What is the answer? What is the answer?
Phreatic lines.
Yes, yes. Simple question. Phreatic line. Below this, there is positive hydrostatic pressure. Okay. Okay. Next question. Soil at the toe of a dam has void ratio 0.62, specific gravity 2.62. Assuming factor of safety of 5, the permissible exit gradient is. Have you solved this question? Anyone?
Yes, sir. Option D, point 2.
Point 2. How have you solved this?
Factor of safety is I critical by I exit.
Factor of safety is I
I
critical divided
by
by
I
I
exit.
exit. Just a moment.
And
Factor of
IC is equal to G minus 1 by 1 plus C.
Yes, factor of safety is equals to I critical by I exit. Very good. And IC, that is the critical exit gradient. We have the formula. What is the formula? Obviously derived from the main formula of India's properties that you can see in check in any standard textbook. G minus 1 divided by 1 plus E, isn't it? G minus 1 divided by 1 plus E. Now, here G is the specific gravity, which is equal to 2.62. Numerator will give 1.62. E is void ratio 0.62. Denominator will give again 1.62. So the value of the critical hydraulic gradient will be equals to 1. So IC equals to 1. So IE will be, that is the permissible exit gradient in this scenario for a factor of safety of 5 will be how much? IC divided by factor of safety. So 1 divided by 5, that gives us 0.2. This is the way you have done, right?
Yes,
So
sir.
yes, the permissible exit gradient is 0.2 over here. Okay, so it will be 5 times less than. So in this scenario, it is 5 times less than the critical hydraulic gradient. Okay, most probably it will be considered to be a safe factor of safety of 5. Next question. Just a moment, let's check. Yes, it is okay. Next question. The value of hydraulic gradient corresponding to zero resultant body force is. Very easy question. What is the answer? Anyone else? I believe only one person is answering. Bhagwan Singh Lodhi.
सर थर्ड वाला क्रिटिकल हाइड्रोलिक ग्रेडियंट.
Okay, okay, fine. Very good. It is critical hydraulic gradient. The value of hydraulic gradient corresponding to zero resultant body force. Okay, that what to say, that kind of signifies the piping failure condition. Okay, so that
ओके
hydraulic
सर.
gradient is called the critical hydraulic gradient. Good. So yes, the value of hydraulic gradient corresponding to zero resultant body force is called critical hydraulic gradient. Next question. Yes, elevation of a point with respect to any arbitrary datum is called. What is the answer? Elevation of a point with respect to any arbitrary datum is called? What is the answer? What are the answers?
Elevation head.
And
Position head also.
yes,
Position. Yes.
yes, very good, very good. So is position head, elevation head. It can be also called as datum head, right? In some places, it's also called as datum head. Okay, so it is elevation, the energy due to the elevation of a point. Okay, it is called position head or elevation head. Pressure head, the height to which the water will rise in a piezometer if it is inserted at that particular point. And what is total head? What is total head?
Sum of the pressure head plus elevation head and velocity head.
Yes, very good. So the Bernoulli's principle, isn't it? The total head will be constant. We know E by rho g plus v square by 2g plus h. Here h is the elevation head or position head or datum head, whatever, and that added with p by rho g pressure head plus v square by 2g, that is the velocity head, will give us the total head. Yes, good. So the answer to this question is elevation of a point with respect to any arbitrary datum is called position head, and also it is called as elevation head. Okay. Next question. Another simple question, very easy. Equipotential lines represent contours of equal density, equal viscosity, equal same path, equal head.
Equal head.
Yes, equal head. The head causing the flow. Okay. Equipotential lines represent contours of equal head. Okay.
So
Yes.
Okay, sir.
I think in the option 4, you have not mentioned which equal heads. It is it's, default. We have to understood that it is all sum of all the three.
Yes,
Otherwise, only
when we talk about equal head, generally we mean the sum of all three. And by saying sum of all three, if it is present, for example, if the water is flowing at datum level, so h is equal to 0, sum of two. So whatever the total head is, okay, that is summed up, and that same same value of the total head, the line joining the same value, that gives us the equipotential lines. So yes, you are correct. When we say equal head, we have to assume that it is the total head we are considering. Because see, if it is not the total head, if I am talking about only the pressure head, the water is flowing, right? It's having a velocity. So I'm talking about the pressure head, but the velocity is different. So total head will be different, right? So how can you say that it is the equipotential lines?
yeah. Here once again, what I am asking is it equal potential head or equal total head or equal pressure heads?
No,
I
equipotential line means equal head. Just a moment.
uh,
I'll just
it
tell you.
is
Yes, yes.
it is equal potential head, sir. P by gamma plus Z.
Okay, you're talking about the exact value.
Yes, sir. Yes, sir. Yes, sir. The option 4 should be equal potential head, I think.
You said P by rho G plus Z.
Yes, sir. That is equal
Yes,
potential head.
yes. In this case, when we say equipotential lines, okay, have I mentioned the velocity? No, it's not the velocity. It is the Z value. Datum, not the velocity over here. This
Velocity head is 0 in soil.
velocity head. Yes, yes. I was thinking about fluid mechanics actually.
Yes,
In
sir.
fluid mechanics, it is the Bernoulli's equation we have. Yeah.
Hmm.
Okay. So yes, this is very nice of you to point out. This is the equipotentialized equal potential head. Equal head means equal potential head over here. As you mentioned correctly, velocity head is 0. So P by rho g plus Z. Okay, P by rho g plus Z in general conditions. But just a moment. I have seen some conditions where the velocity is being calculated. Just give me a moment. No, the velocity is not always zero, I believe.
Always zero, sir. In soils, it's negligible.
Yeah, soil is negligible, but when I consider the equipotential lines, I'll just tell you. There is isotropic soil, there is anisotropic soil. Both have different scenarios. Velocity potential. There is a stream function, seepage pressure, exit gradient, phreatic line. Yes. The velocity of flow in soil is generally negligible. Okay,
Yes.
your
Yes,
mention
sir.
is correctly, but it is generally negligible. It cannot be taken as zero. Here in this question, when I talk about equipotential line, this potential equipotential line means potential head. Okay, and when I say equal head over here, okay, okay, this question could have been modified as equal potential head, but again,
Yes, sir.
equipotential line, if we consider over here the velocity almost equal to zero, negligible, then we are left with the pressure head and the datum head.
Beautiful.
Okay, so I might have misplaced the term datum head for velocity head. No, it is not that. I just take that back. It will be a summation of uh, this P by
These
rho
two.
g pressure head and the datum head. Okay, good. So
Yes, sir.
equipotential lines represent contours of equal head, and by equal head we means equal potential head, which
Potential
is a
heads.
summation of the pressure head and the datum head. Okay,
Yes, sir.
yeah, thanks.
Welcome, sir.
The next question. Yes. The path along which individual particles of water seep through soil is called. What is the answer?
First and last.
Flow lines and streamlines. Yeah, flow lines and streamlines. Okay. Next question. Grains in the soil below hydraulic structures get lifted when the critical hydraulic gradient is greater than the exit gradient. True or false?
It's true, sir.
True. Critical hydraulic gradient is more than the exit gradient. That is the exit gradient less than the critical hydraulic gradient. Will the soil get lifted due to piping failure?
It is true only, sir. Factor of safety is IC by I exit.
Yeah, factor of safety is IC by IE over here. So factor of safety in this condition is more than 1, right? So if it is more than 1, will the soil
Sir,
get lifted because of piping
no,
failure?
no, sir. When factor of safety is more than one, it cannot lift. When factor of safety is less than one, it will lift.
Yeah, so in this condition, see critical hydraulic gradient I have said greater than the exit gradient. So factor of safety will be more than 1, right? So how can the soil get lifted due to piping failure? How can piping failure occur in the first place? The exit gradient has to be has to be more than the critical hydraulic gradient, isn't it? If this is otherwise, then the factor of safety will be less than 1, isn't it?
1 second, sir.
Yeah, take your time, take your time.
Yes, sir. It's false.
Yes, it is false, right?
Yeah. Factor of safety is more. It is a proportion to I critical.
Yes, so I critical, if it is more, factor of safety is more, there will be no piping failure, the soil won't get lifted up. And
Yes,
if
sir.
it is less, that is the exit gradient, the condition is the gradient with which the soil is seeping upwards is called the exit gradient. That has to be less than the critical exit gradient. If it is more, then piping failure is occurring. Isn't it? Could you follow?
Yes, sir.
Yes,
Understood.
yes, 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 good. So the answer of this question is, this statement is actually a false statement. Okay. Next question. Yeah, next question. The portion between two successive flow lines is called, what is it called? Portion between two successive flow lines.
Flow channels,
Yeah, flow channel. It's also called,
flow path.
yes, very good. Also called flow path. Okay. Next question. In a flow net, there are 4 flow paths and 15 equipotential drops. If the head loss is 3 meter and K is 2 into 10 to the power minus 5 meter per second, estimate the quantity of seepage in meter cube per second. Have you solved it? What is the answer?
C, sir. I got C.
Formula is Q equals to
K into
H into,
NF by ND.
what is NF? Number of flow
Number of
paths.
flow channels or
Yeah,
flow path.
flow paths, or, and ND is number of equipotential drops. So here it is equals to 4, here it is equals to 15. K I have given 2 10 to the power minus 5, and H is equal to 3. Putting all the values, I think you're getting C, right? 1.6 10 to the power minus 5.
Yes, sir.
Yeah, meter cube per second. Good. So the rate of discharge is equals to coefficient of permeability multiplied with the head multiplied by the ratio of number of flow paths to the number of equipotential drops. Okay. Okay. Next question. For a two-dimensional flow, it is assumed that the porous medium is incompressible. Is this statement true or false? This statement is true or false?
I think it is true, sir.
Yes, yes. Basic assumption of the Darcy's law, because if the porous medium is the otherwise, if it is compressible, what will happen? The pore spaces will vary, right? The area will vary, and then we will not be able to use the Darcy's equation Q equal to KIA. Okay. So yes, for a two-dimensional flow, it is assumed that the porous medium is incompressible. It is an assumption of the Darcy's law. Next question. Seepage pressure is, basic definition.
Option C.
Yes, pressure exerted by percolating water on the soil. Pressure exerted by the percolating water on the soil. Good. Okay. Next question. Yes, homogeneous earth dam 2 meter high with 2 meter freeboard having 25 equipotential drops and 4 flow channels. Coefficient of permeability is 3 10 to the power minus 3 centimeter per second. Calculate the discharge in meter cube per second. Which answer you have got?
Second answer, sir.
B, right? 0.00024. Yes. So what is the value of H over here?
50 meters, 50.
Yes, 52. That is the height minus the freeboard. How does it look like? So dam is the upstream, the downstream. So this is the water level. This is just for safety purpose. If its water level rises up, then water is released from here. This is the freeboard. This is the entire height is 52. This is 2. So the height of water, that is the head causing the flow, is 50. And again we use the same formula. Rate of discharge equals to K H NF by ND. 3 10 to the power minus 3, value of K H equal to 50, NF equal to 4, ND equals to 25. Putting on the values in this formula, we get 0.00024 meter cube per second per meter length. Okay. Is it clear?
Yes, sir.
Yeah. You have solved this problem, so you are saying it's clear, but other person is not saying anything. So, and it happens in the other
Bhagwan,
classes.
Bhagwan Singh.
Yeah, it happens in the other classes also. One or two people are only interactive, and other people don't interact. Okay, it's fine. Anyway. So yes, the next question is which one among the following is a scalar function of space and time whose derivative with respect to any direction gives the fluid velocity in that direction? What is the answer? And the one who is not answering, please. Yes, Bhagwan Singh. Good.
Velocity potential.
Velocity potential. Yes, so you know the answers. You should speak up more often. Velocity potential. Okay. How do we define the function? Velocity potential.
Velocity potential.
Yeah, like how do we define the function? It's a
That
product
is
of,
the scalar function.
no, no.
Scalar function and
Okay, wait. I'm saying. So this is the way we define product of the coefficient of permeability and the head. Okay, causing the flow. Now what I have mentioned over here is the derivative with respect to any direction. For example, if we differentiate this, and why do I write this like this? Because it is a partial derivative, obviously. It is a constant. Head causing the flow divided by the thickness or length. This is what? Gradient, right? It is equals to velocity in the x direction, isn't it? Is this derivation clear?
okay, sir.
Sir,
Yes.
what is the source you are following for this particular topic, sir? Not chapter, only present topic about the
I
potential.
I always follow soil mechanics and foundations by BC Punmia.
Visible. Okay,
Yes,
okay.
and
Right.
sometimes I also follow Gopal Ranjan Rao, because see, these two books, BC Punmia and Gopal Ranjan Rao. Okay, they are significant in their own way. Like if you want to have a very good experience with the numericals, preparing yourself for competitive examinations, along with getting the conceptual insights. Okay, BC Punmia is the best option. But in Gopal Ranjan Rao, the theories, the concepts, they are written in a much intricate way. Okay, in a very much detailed way. Might be the numericals will not be as what to say vigorous, or as, you know, there are not
Okay.
as many numericals as there are in BC Punmia, and
Yeah.
I don't believe that the presentation of the book Gopal Ranjan Rao is as good as BC Punmia, but the theory and the concepts are in some chapters I've seen to be very well written. But anyway, I mainly follow BC
Thi-
Punmia.
This
Okay,
top, this slide, sir. I am asking this slide particularly.
this particular slide, I think BC
Oh.
Punmia have followed. Anyway, you
Okay,
can
sir.
find in BC Punmia or Gopal Ranjan Rao same thing. So is this
Thank you.
derivation clear? Like the definition and the derivation?
Yeah, it's clear. I want to still further go ahead with this because very rarely they are asking a questions on this topic,
Yeah.
even in NPTEL exam as well
Hmm.
as in other competitive exams.
You get numericals, like not in, in your I don't believe, like when I was in BTech also, numericals from this
Mm.
particular topic I did not get. But then in other competitive examinations, gate and all, ES and all those things, this
Okay.
both in fluid
Yes.
mechanics and soil mechanics,
Okay.
this velocity potential,
Mm.
steam function, their definition, their derivation, and numericals, they are very important. So
Okay,
yes,
sir.
if you
Okay,
are to
sir.
go ahead, that's a very good decision, because you might be needing this for upcoming
Yes,
exam
sir. Yes, sir. Yeah.
examinations
Yeah.
only.
Thank you, sir.
Yeah. Okay, so this is the definition of the velocity potential. Next question. Yes, portion between two adjacent equipotential lines and adjacent flow lines is called equipotential lines, flow lines. What is this called?
Flow field.
Yes, flow field or field. Okay, you can call it as simply field also. This is the flow line. And what is this called? This space is called flow channel, right? Or flow path. Okay, so yes, portion between two adjacent equipotential lines and adjacent flow lines is called field. Good. Next question. Hydraulic head that would produce a quick condition in a sand stratum of 2 meter thickness if G equal to 2.7, E equal to 0.7. What is the answer? Hydraulic head in meter. Definitely. What is the answer you have got?
Close to once.
Yes,
Close to one, sir.
1. I don't believe that is the correct. I'm talking
Yeah.
about the hydraulic head.
Sorry, it is a 2 meter. It is 2 meter. Sorry.
Yes, yes, yes,
Yes, sir.
yes.
It is a 2 meter.
2 meter. How do you solve this? You first calculate the critical hydraulic gradient, which is again G minus 1 by 1 plus E. You'll get again over here as 1. Okay. And the critical hydraulic gradient equals to the head causing the flow divided by the length of traverse of the length of the flow, that is the thickness of the soil. So the head causing the flow will be equal to IC into L. Okay, the thickness is 2 meters, so 2 into 1, 2 meter. Clear, right?
Yes,
This,
sir. For this type of questions, answer will be in the question only, sir.
yeah, answer will be in the question only, like, yeah, because I have given in all the questions to make it simple, like this value
Yes, sir.
will be deduced from
Uh,
1 only. Okay, and in this chapter, basically, with respect to this critical hydraulic gradient, you have similar kind of questions like I've given in many books. They have
yes.
similar kind of questions. So it is, I believe it is important, if you venture into the zones of that potential velocity potential steam function, that will cover up both of fluid mechanics and soil mechanics, common for both. Okay, anyway, let's go to next question. The critical hydraulic gradient for a loose deposit of sand. Again, easy question. What is the answer? Common answer. Hello? What is the answer?
Yes, yes, sir. One,
Sir,
sir.
answer is 1.
Yes. Yes. Anything else you want to say? Okay, fine. Yes, answer is 1. G minus 1 by 1 plus E. G is 2.67. E is 0.67.
Yes, sir.
Yeah. Okay. Fine. Next question. Yes. Have you solved this?
Yes, sir.
What is the answer you have got?
Third answer, option C.
Yes. Option C. Why? Because here this hole was drilled prior to the excavation. So when I say that water has started entering the trench from below, and I've already mentioned previously that there was a crack, that means it is a case of piping failure, quicksand condition, right? So over here we have to consider that effective pressure equal to 0, isn't it, at this level of sand. And what does it mean, effective pressure? Total pressure minus the pore pressure. Total pressure minus the pore pressure. Total pressure is the pressure exerted by the clay. That is Z gamma sat, isn't it? Z gamma sat. But the pore pressure over here will be equal to gamma W times the height of the water that has risen in this borehole, isn't it? Is it clear, or there is a doubt
Yes,
regarding this? Yeah, clear, right?
yes, sir. Yes, sir.
What I'm saying?
Clear, sir.
Yes. So just solving this equation, you will get HW, the height to which the water has risen over here, will be Z gamma sat divided by gamma W. Okay, gamma W is 10, Z is 4.5, and gamma sat is 18.5. You will get 8.325 meter. Again proving that it has risen more than the value of Z. Okay, so this seepage pressure, it is counteracting this overburden pressure from the clay, giving rise to quicksand condition, because of which water has started entering the trench from below, from here. Okay. Okay, so nice to know that. Okay, just a moment. Yes, so I'll just repeat this once again. The OBS record has stopped changing slides. So whatever I've said, the effective pressure equal to 0. That means total stress minus the pore pressure. Here the pore pressure is equals to HW gamma W times the height to which the water has risen in the borehole which was drilled prior to the excavation. Solving this equation, you get the height of the water HW as 8.325 meter. Okay, so I think I'll go to the last question now. We first check whether it is, yes, it has. Okay, so water has flowing at a rate of 0.04 ml per second for detection to fine sand. Coefficient of permeability is 2 10 to the power minus 3 centimeter. Sample thickness is 10. Cross sectional area is 45. Saturated liquid is 1.93. What is the head causing the flow? What is the head causing the flow?
4.44 centimeter.
Very good. U equals to KIA. Okay. So what is I? I equals to H by L. So rearranging the equation, I equals to H by L. So H equals to will be discharge thickness divided by K into A. Putting all the values. What is the value of L? 10 centimeter. A is 45. Q is 0.04 and K is 2 into 10 to the power minus 3 centimeter per second. We get 4.44 centimeter is the value of H. The next one, effective stress at the bottom of the soil. What is the answer you have got?
4.86
Very good, very good.
grams per centimeter square.
Grams per centimeter square, yes. Very good. So, at the bottom of the soil, we have to remember over here that the water is flowing at an upward direction. Okay, water flowing at an upward direction. So, in this case, in general case, what we do that we for finding out the effective stress, what do? We subtract total pressure minus the pore pressure. Okay, total pressure minus the pore pressure. But in this case, since water is flowing in an upward direction, the water has a different head. Okay, so that head over here is H. So the upward force over here will be the head causing the flow multiplied by the unit weight. Okay, or I'll just simply write density. It is better because I'm showing it in gram per cc, the density of water. Okay, upward force, the density, head causing the flow multiplied by the density of water. What is the downward force over here? Downward force is the thickness of the soil, obviously, the submerged density. This submerged density. Why? Water is flowing upward. Okay. It is not contributing to total stress. Water flowing upward, not contributing to total stress. So, effective stress. For the effective stress, the downward force will be the submerged unit weight multiplied by the thickness of the soil. Now, what is rho dash the submerged unit weight?
0.93.
Yes, 1.93 minus 1, 0.93 gram per cc, obviously. Okay. So, over here, the effective stress, that is sigma, at the bottom of the soil layer will be equal to what? Will be equal to the downward force minus the upward force, isn't it?
Yes, sir.
Yes. So you subtract downward force, that is 0.93 into thickness is 10 centimeter. So 9.3 minus 4.44. We get 4.86
0.886.
gram per cc. So, okay, the sum I have done, you have also done the same thing, but the explanation.
Sorry, sir. It is a
Yes.
gram per centimeter square.
Oh, sorry.
Not
It is the force. Yes, sorry. It is gram per centimeter square.
square.
Yeah. Okay. So yes, I have done this sum. You have also done this sum, but the explanation, what I have explained right now, is it clear, or should I explain again? Why I am considering in the downward force this rho submerged. Total stress minus the pore pressure we generally consider, but because the water is flowing in an upward direction, it is not contributing to total stress, and hence we have to consider the total pressure, in this case the effective density. Sorry, not effective density, the submerged density. Okay, so submerged density multiplied by the thickness gives us the total downward force, and that subtracting the upward force we get the effective pressure. Okay, so this is a, when there is seepage in the soil, the scenario is different from when we are calculating the stress in general scenario. Okay, so there are many scenarios right now. Up till this point, there is total pressure, effective pressure, there is soil suction, Okay, and then there is seepage conditions. So I think that these three different scenarios, how you need to interpret these scenarios, understand them separately. I think it is clear to you.
Yes, sir. For me, it is clear.
Yeah. Okay. Is there any doubt, any doubt regarding any other question?
No, sir.
Okay, fine, fine. So I believe that just a moment, I'll just switch to the. Yes, I believe the session was it gave you some insights into the concept of seepage, isn't it?
Yes, sir. Yes, sir.
Okay, fine.
Sir, a small clarity required, sir.
Yes, small clarity for what?
And I don't know why this chapter was right now you have selected, because is it you have to follow the sequence of the faculty
Yes, yes,
professor,
yes. I
but the
have to.
chapter was not covered, no, sir.
I don't know because let
That
me
is why I'm intimating you.
let me check. I'll just switch to the.
Right now, compaction is over.
Just a moment. Just a moment.
Yes, sir. Yes, sir.
Someone is joining now. Oh my God. Who is this? Tamil Selvam. The class had started from 6 o'clock. The class had already ended. Please mute yourself. Um, Tamil Selvam, please mute yourself. Yes, as I can see, okay, as I can see, the class who had asked the question about the session following the syllabus.
Yes.
Yeah, as I can see that this should be the sixth discussion session. Okay, and if I check the syllabus, just a moment.
Week 6 was compaction, sir. Actually,
Wait, I'm checking this syllabus. No, as I can see, soil compaction. This is geotechnical engineering one, right? The
yes, sir.
subject. So I can see that week 4 was soil compaction, which is already over. Which is already over. Week 5 was soil water statics.
Yes,
Soil
sir.
water statics, and week 6 is flow through soils, quicks and condition. Week 7 is permeability.
No,
Week
sir. No,
8,
sir. There was here, as per the professors, what he is covering.
the professor's name I think is Devendra Naran Singh, right?
Yes,
DNC sir.
sir. Yes, sir. Week
Okay,
6
okay.
was compaction. Week 6 was
Wait.
compaction.
Okay, I have already downloaded the syllabus, but I'll
Mhm.
again, once again, check in the Google. Just a moment. The current syllabus in the website. Okay, give me a
You are
moment.
going as per syllabus.
I am going as per the syllabus. Yes, I am going as per the
Okay, okay.
syllabus.
But professor was maybe, I don't know, professor was not following the syllabus. But
Okay,
week
then
6 was compaction as per him.
that I'm not intimidated about how the professor is going, because I'm not interacting. The scholars they don't interact with the professors.
Mm.
Okay, so I think that might be an issue, but anyway, just give me a moment. So here, this is CE 29, I believe. Yes, CE 29. Technical engineering one. Mhm. Yes, geotechnical engineering one syllabus. Yes, when I'm clicking on the syllabus, it is showing the same thing. Week 6, flow through soils, quick sand
You
condition.
You are correct, sir. You are correct. As per week 6, as per the syllabus, is flow through the
Yes.
soil and
So
quicksand condition.
yes. So the professor, I think he has started another
Professor,
chapter before starting this chapter.
yeah, actually, flow through soil he didn't cover till now.
Okay, okay. But you could answer all the questions, no? So
Yeah, yeah, that's okay, sir.
yeah. So
I am telling for audience, mismatching will be there. That is why.
yeah, that is the thing. But again, at the end of the day, I think many people like it happens like whenever in these classes, in the initial 1 or 2 classes, there are
Hmm.
like 10 or 12 students they join. Okay, but after that, it reduces to 2 or 3 because they already know that they are going to get the YouTube materials and all those things. So the attendance decreases. So anyway, I
Hmm.
think people will see the YouTube videos. They can see it later also after they sorry
Okay.
after
In that
they
case,
after they cover the chapter. It is covered by the professor. So anyway, it is okay.
you have not covered still now soil compaction, sir.
Yeah, I've covered soil compaction.
Compaction is over. Then what is
Yes.
missing from your side?
As if you go as per the
Mhm.
syllabus given in the NPTEL website, I
You
would
are
say
following as per that.
yes. Till chapter 6, I have followed.
Okay.
I'll
Okay.
just a moment. If you give me just one moment, I'll just tell you because I've already uploaded the videos. It is there. So week one, I believe it was the origin of soils, right? Origin of
Yes, sir.
soils, week one, and then it week one origin of
Which?
soils, yes, and then it was the basic relationships in these properties, that chapter.
Yes, sir.
Then it was, I believe, soil structure, soil classification, week
Yes,
3.
sir.
Week 4 was soil compaction, and then week
Hmm.
5 it was soil water statics, that is the
Yeah,
effective pressure, that chapter.
you are following exactly.
Yes, yes, yes. So that will be what I follow and what will be done as per the
Okay.
scenario in this session. So week 7, whatever it is given in the syllabus, that will be done in the coming Friday session also. Okay,
Okay, sir.
okay. So thank you once again for making this class interactive, and thank you for attending the class. We'll again meet on the coming Friday with the 7th session. Okay.
Thank you, sir.